Physics, along with the Indian Association for Physics Teachers, Mumbai chapter has organized this very amazing series of RJC physics lectures in collaboration with IAPT Mumbai chapter. And we are very thankful to them, and also thankful to the very illustrious resource persons who have agreed to deliver a talk and then share their experiences with all the youngsters. And I think from the questions which are coming after each and every session, it's very encouraging. So today we have with us Dr. Anwesh Mazumdar from our very neighbor, that is the Homi Bhabha Center for Science Education, where we always look forward to them like a destiny, we say, for motivating students to take up science and to take up small projects. And on behalf of Indi Vidya Prachar Samitis, Ram Niranjan Junjanwala College, I extend a very warm welcome to Dr. Anwesh and to all the participants and the members of IAPT. I would also like to thank them for allowing us to host this entire session, to Dr. Rekha Ghorpade, the head Department of Physics, for being an encouraging force for the entire team. So with this, I extend a very warm welcome to you, and especially to Dr. Anwesh. Over to you, Rekha Madam.
Thank you, Madam, for your encouraging words. May I call Professor Shekhar from Mumbai RC, IAPT Mumbai RC, to say a few words about IAPT. Shekhar. I suppose Shekhar has not joined?
Shekhar has not joined.
Okay. Can you, even Atul is not there?
No, Atul is also not there.
Okay. If Bhole sir is there, please unmute him so that he can start the lecture. So that he
Bhole sir is also not there. Bhole sir is also not there.
Bhole sir is there. K Bhole.
Yes, Bhole sir is there.
Yeah, just make him co-host so that I can request him.
Yeah. Bhole sir, co-host.
Yeah, Bhole sir. Hello. Can you hear me, Bhole sir?
Hello. Yeah.
Yeah. Sir, I would like to request, because Shekhar has not joined, he was to do the honor. I would like to request you to please say a few words about IAPT. And
Shekhar is very much there.
No, sir. Shekhar
is there.
Just now he must.
Okay, no problem. I'll start.
Yeah, Shekhar Awala. I think Kiran Shekhar is there. Just a minute.
Unmute him.
Yeah.
Shekhar is there.
शेखर हॅलो हा सांगितलंय मी आता तुझं नाव सापडत नव्हतं या शेखर SHAKER शेखर अवाला या Is he meant?
Yes, done.
Shekhar, unmute yourself.
Yeah, good afternoon, everybody. Let me introduce IAPT. Mostly, I think IAPT has been introduced. I'll talk of Mumbai Sub-RC. Mumbai Sub-RC has been conducting this various programs for teachers and students. And for students, I would like to specifically say IAPT does this NGP examination in the third week of January. And I think more students should take up that examination as it would help them because it's an all India examination. So you can find your ranking overall in the country. And let me introduce the Mumbai Sub RC also because they have people be working behind the scenes. So our president, Mumbai Sub RC, Dr. Atul Modi, Secretary Mahesh Shetty, Treasurer Madam Rekha Madam, myself, and Bhole Sir, Devidas Gulwade, Amit More, and Swapnil. So this is the sixth lecture in the series 1, and we would like to have a few more. And the series 1 is in collaboration with Junjunwala College. So thank you, madam. So,
yeah, thank you, Shekhar, for your introduction of IAPT. Most of the teachers, there may be some new participants. For them, it was really helpful. And now I request my colleague, Professor Sandeep Hinge, to please introduce our today's guest. Sandeep, please.
Yes, madam. Am I audible?
Yes.
Yeah, thank you, ma'am. A very good evening. On behalf of Hindi Vidya Prachar Samiti's Ram Niranjan Junjunwala College, Autonomous, in association with IAPT, Mumbai chapter, I welcome all for physics lecture series, lecture number 6. Now here I also welcome our director, Dr. Usha Mukundan, principal Dr. Himanshu Davda, and all my colleagues. Now it is my great honor to extend a warm welcome to today's resource, Dr. Anwesh Mazumdar. Now let me introduce his research experience. He obtained his PhD from TIFR, then postdoctoral experience at various observatories such as Paris, Meudon, Catholic University, Lyon, Belgium, and Yale University, USA. Now, sir, research interests that include stellar astrophysics, in particular using oscillation in stars to understand their internal structure. Now, his other research interests are in domain of physics education. Now, presently, sir is a national coordinator of Science Olympiad, India, and he is a faculty member at Homeopathy Center for Science Education, TIFR. Now, before this, there's a small note for all the participants. You may type your question and doubt in chat box of Zoom and YouTube so we can discuss and answer it at end of the session. Now, sir, I would like to hand over the session to you. Sir, please, sir.
Thank you.
Yes, Anwesh.
Thank you. Yeah, am I audible?
Yes.
Yeah. So thank you, Dr. Hinge, for the very kind introduction. And let me first begin by thanking IAPT Mumbai chapter and also Junjunwala College, in particular Professor Ghatkopar and Dr. Shekhar, for inviting me to give this talk today on exoplanets. I'm very happy to be here. Okay, so let's begin. Let me first share my screen. Okay, is my screen visible?
Yes.
Okay. So, so today I shall be talking to you about exoplanets, which is actually just a short word for extrasolar planets. And what I shall be talking about is mainly the methods of detection of exoplanets. I shall not have time to go into the structure and the characteristics of exoplanets, but I will also talk about the possibility of extraterrestrial life in these exoplanets. Okay, so first of all, what are exoplanets and why do we need to study them? So as I said, extrasolar planets are planets orbiting around stars other than the sun. Okay, and we must keep in mind that a star may harbor one or more planets. As we know, our sun has 8 planets, and similarly, other stars may also have multiple planets. So why are we interested at all in exoplanets? Why do we study exoplanets? So first of all, planets help us understand their host stars better. because from the planetary composition, from the orbital distances of planets and the age of the planets, we can make many interesting inferences about the stars themselves, about the host stars. So that is one reason. And of course, the planetary systems throw light on the formation mechanism of our own solar system and the Earth. If we look at other similar stars and similar planetary systems, perhaps we'll learn more about how we came where we are today. Okay, and but all this is, I think, drives towards one of the main questions that has been at the back of people's minds for a very long time, is that whether there is life elsewhere in the universe, or whether the Earth is such a unique place in the whole universe where we have life, and indeed intelligent life, or whether that there is life elsewhere in the universe. So the answer to this question is not known yet. We cannot say definitively yes or no to this, but there are some indications about whether life can possibly exist, and we shall come to those in this talk. Okay, so about today's talk, one of the primary focus is that how do we detect planets around distant stars? Okay, so planets are difficult to detect around distant stars, and why? Because the stars are very bright, right? The stars are 1 billion times brighter than the small planet, which might be very close to the star. So if you notice that if this lighthouse light, this very bright light represents the star, and then the planet is something like a very small light bulb, which is just behind the star or just alongside the star. So there are two problems here. One is that the planet is hidden in the glare of the star. And secondly, it is too close to the star. So we cannot resolve the planet separately from the star. So it's very difficult to see a planet distinctly from the star. Okay, so these are the main challenges that we have. Okay, so there are several methods to detect exoplanets, and among them, two are primary methods, and two are the methods which have borne us most results. And I shall be talking mainly about these two methods, which are in the first two, that is the radial velocity method, and the second is the transit method. Many of you might be familiar with these terms and even the methods themselves, so please bear with me when I describe these. There are some other methods, namely direct imaging and astrometry and timing variations and gravitational microlensing. These are sort of minor methods. Of course, planets are detected using these, but compared to the first two methods, the number of detections with these latter four are much less. So I will only talk about them if time permits. Otherwise, I will skip over them. I do have some slides on them, but let's see how it goes. Okay, so first let us start with the radial velocity method. So what is actually the radial velocity method? This is also known as a so-called Wobble method. And the reason is this, that as we know that a planet and a star, when they orbit each other, they don't, I mean, it's, although commonly we say that the planet goes around a star, we know as physicists that that's strictly not true. Both of them orbit each other around their barycenter or center of mass, right? Now, typically the star is very heavy compared to the planet, and therefore this center of mass of the star-planet system lies almost at the center of the star, okay? But of course, it is almost at the center. It is not exactly at the center. And therefore, as the star and the planet go around each other, the star also wobbles a little bit because its center goes around the center of mass of the planet. So, or the system, sorry. So let me first here break a bit and show you animation, which will perhaps help. Or before that, okay, maybe I'll just finish the slide first. So what happens is that as the planet and the star go around each other and the star wobbles, the light that we receive from the star. Now, as we know that a moving source of light, if we look at at the frequencies of that light, they undergo Doppler shift, right? So the light received from the star undergoes a small Doppler shift because of this wobble of the star. Now, I emphasize here again and again that we are looking at the light from the star, not from the planet. Of course, the planet and the star cannot be resolved separately, but since the star's light is much brighter than that of the planet, so what we essentially get is the light from the star. Okay, so here is a schematic here where you can see that this is the, let's say, the center of mass of the star-planet system. This blue dot here is the planet. The red big ball is the star. And as they go around the center of mass, now if we are looking, which is, let's say, in the downward direction of the observer, we are looking from the downward direction towards the star. So when the star, at some stages of the orbit, the star is moving away from us, and therefore this light is red-shifted. At some other stages, the star is coming towards us, and therefore the light is blue-shifted. And we measure that in this spectrum here. If you look at these spectral lines here, let's say this double line close to the boundary of the red and the yellow zones. So this is when the star is, of course, moving perpendicular to our line of sight. There's no Doppler shift. So this line, this absorption line, is almost at its laboratory frequency, laboratory frame frequency. But when there's a red shift, it moves towards the red. And when there's a blue shift, it moves towards the blue. And this is what we measure. This Doppler shift is what we measure in this method. Okay. Now, just to note, the radial velocity in astronomy is just a term for line of sight velocity. What we understand as line of sight velocity, that is a celestial object's velocity when it is directly coming towards us or going away from us. Okay, that is in astronomy, astronomers call that radial velocity. Okay, now let me quickly show you the animation, which is just a very short one. So as you can see here, so this is the planet and this is the star. They are going around the common epicenter. Now look at this wavelength here and notice that we are looking at the starlight. So now the star is coming towards us, therefore the wavelength is blue shifted. When the planet comes around, now the star is going away from us and it is red shifted. The planet's light, of course, is oppositely shifted, but we are not looking at that. We cannot look at that. Okay. So this is basically what is happening. So we are looking at this Doppler shift. Okay. Now again, let me go back to my presentation. Okay. So so the amplitude and the period of this velocity, of course, from the Doppler shift, we can immediately calculate the velocity of this wobble, and from that we get the characteristics of the planet. So how do we get this? So before we come to that, first of all, we must satisfy ourselves that what is the kind of data that we get. So what we get is basically, if you look at, so here is the x-axis is, let's say, phase or time. And on the y-axis, we have this radial velocity, which has been obtained from the Doppler shift. And for a circular orbit, the radial velocity or the line of sight velocity follows a sinusoidal pattern, right? So this is where the planet is going away from us. This is where where the star is going away from us. This is where the star is coming towards us, and the zero crossing is where it is moving perpendicular to our line of sight. So for a circular orbit, we get a perfect sinusoidal pattern. This can be shown mathematically very easily. However, planets usually are not in circular orbits; they're in elliptical orbits. Depending on how much the ellipticity is, if the eccentricity is significant, then we get something like this. So we still get a periodic signal, but it is not sinusoidal. But it is possible to get actually the eccentricity from this as well, from this pattern. Okay, so this is these are actual data. So this is the kind of things that we observe. Now, there is one complication in this, is that in the animation that I showed you, you would have seen that the perspective changed midway through the animation. First, we are looking at when we are looking perpendicular to the orbital plane, and then we are looking parallel to the orbital plane, and then we are again looking at the end perpendicular to the orbital plane. Now, of course, for a distant star-planet system, it is not necessary that our line of sight is along the orbital plane, right? In general, the orbital plane will be inclined at some angle with our line of sight. Let's say I is the inclination angle, which is basically the angle between our line of sight, which is this horizontal line, and the normal to the orbital plane. This is how we measure inclination. So inclination of I equal to 90 is the edge on view, and I equal to 0 is the face on view. Now, as the star goes around this is the center of mass, let's say. So as the star goes around this, of course, the star has an orbital velocity, let's say, of v. But what we are measuring is only a component, V sin I, right? We are not measuring V, we are looking at V sin I. And this complication remains with us because we don't know the I ab initio at least. Okay, there are methods to determine the I, but ab initio, at the beginning, we don't know the I. So what we are observing actually is V sin I. This must be kept in mind. Okay, so let's look at the mathematics a bit. So we observe two quantities. One is the period T of the orbit, which is very easy. So this is a schematic diagram, very similar to the data diagram that I showed you earlier. On the x-axis is time, on the y-axis is velocity. So just the period of this gives you the periodicity of the wobble, and that must be the same for the planet because they're going around the center of mass, right? So this is some observed quantity. This we can immediately get from the periodicity of the data. The other thing that we observe is the amplitude of the wobble, which is K in this diagram, which is V star sin I. I explained the sin I part, and V star is the velocity of the star. So then, so first of all, we can use Kepler's third law. We all know Kepler's third law. So we can get the orbital radius of the planet from its period through this, right? Notice that we need to know the mass of the star here. The mass of the star enters this formula. Okay, so the mass of the star, we must have some estimate of the mass of the star at least, or more precisely through other methods, we can get the mass of the star. But once we know that from the period, we get the orbital radius. Now, the planet centripetal acceleration is due to gravity, right? So due to the gravitational attraction of the star, and we all know this formula very easily. So the velocity of the planet is equal to root over g m star, where m star is the mass of the star, by r, where r is orbital radius, right? So one can get the orbital velocity of the planet knowing r from the period. And then we can apply the momentum conservation. And so then we can get the mass of the planet, because now we have m star, we have v star, which is observed, and then vpl, there's a planet velocity, which we get from here. Now, notice that we do not really observe v star, we observe v star sin I, which is k, right? So we can get only mpl sin I, right? So therefore, we get the mass of the planet rather times sin I. So we get only a lower limit to the mass of the planet because of this inclination factor, right? Of course, for a known mass of the star. Okay, so this method gives us the period, the orbital radius from that, and the mass of the planet, or rather a lower limit to the mass of the planet. So we can characterize the planet also from this. So this method, as you perhaps know, excuse me, as you perhaps know, this the last year's Nobel Prize in Physics in 2019 went to Michel Mayor and Didier Queloz for the discovery of an exoplanet orbiting a solar-type star. This discovery was actually made long back in 1995 with the discovery of 51 Pegasi b. This b is, so astronomers name the planets like B, C, D, etc. The A is reserved for the star, and 51 Peg is just a name for some, this is a number, and Pegasus is a constellation. So this is a star which is going around, this is a planet which is going around 51 Peg, which is a sun-like star about 50 light years away from us. This actually is the original data from the original paper in 1995 from Mayor and Queloz. And they used the LOD spectrograph on the Observatoire de Haute-Provence telescope in France. This is the telescope. This is, of course, they're pictured perhaps after the Nobel Prize, much later, because Michel Mayor was much younger when he made this discovery. So, and what they found was that this is about a half Jupiter mass planet, about 0.5 Jupiter mass planet, but in a very close orbit. The orbital period is only about 4.5 days, which means about 0.05 astronomical units. Okay, so pictorially, this is what it would look like if you replace the sun. Let's say, so this is a pictorial diagram of the solar system, and this is Mercury's orbit, and this is Venus's orbit. So if you replace sun with 51 Peg, this star, and then you put the planet 51 Peg b, this is how its orbit would look like. So it's much, much closer than even Mercury, our closest planet. Okay, so this is how the picture is. And this discovery was significant because this was the first discovery of a planet around a sun-like star. Before that, 1 or 2 discoveries were made, but around very different kinds of stars. So this completely changed the game, and it was proved that one can use the radial velocity method to detect exoplanets, and after that, many exoplanets have been detected using this method. Excuse me. Okay, let me just take a sip of water. Okay, so now the point is that the amount of the wobble or the radial velocity is directly proportional to the mass of the planet and inversely proportional to the square root of the orbital distance. This one can easily get from the formula that we discussed earlier. So this means that this method is most sensitive to massive planets, big planets, where this MPL is large, and where this R is small, that is massive planets close to the star with small orbital radius. And these are called hot Jupiters because Jupiter is a big planet, as we know. So, but hot. Jupiter is cold, of course, in our solar system because it's far away from the sun. But hot Jupiters are Jupiter-like planets close to the star. So this radial velocity method typically favors hot Jupiters. Okay. Now, of course, this picture has changed a bit because our sensitivity has improved. How does that matter? Because the best spectrographs today can measure velocities of the order of about 3 meters per second, stellar velocities. So these are the best spectrographs in the world, actually, which is just at the detection limit of terrestrial planets in Earth-like objects. Now, in this graph, if you see on the x-axis is the semi-major axis of the planetary orbit. On the y-axis is the mass of the planet in terms of Jupiter mass. So if you look at this, so this is these red dots are the solar system planets. So this is Mercury, this is Venus, this is Earth, this is Mars, then this is Jupiter, and this is Saturn, then this is Uranus and Neptune. So these are the solar system planets. These blue dots are the planets that have been detected through the radial velocity method. So as you can see that we detect mostly heavy planets, okay? Almost all of them are heavier than Jupiter. And initially we could detect only these planets that is also very close to the star, that is the semi-major axis is small. But now with increased sensitivity, we can detect even these, okay? So 51 Pegasi B would be somewhere around here, okay? It's about somewhere around here it will be. Whereas now we can even detect this. So where does Earth stand on this? So the Earth-like planet at the in terms of mass and the semi-major axis is this. If you look at here, we are just, I mean, approaching that. We are not, it's still a far way to go. Okay. Some spectrographs today can go down to even 1 meter per second. And this green line roughly shows that limit. Okay. But these red ones are the current detection limits. So the summary is that we can detect large planets in close orbit. So the advantages of the radial velocity method is that this is, of course, distance independent because we are doing spectroscopy. And these observations can be done from the ground. Okay? We don't need to go to space for these observations. But these require very high signal to noise ratio because we are measuring extremely small velocities. You can imagine we are measuring velocities of the order of meters per second. This provides only a lower limit to the planet mass because we don't know the inclination. And this method does not work for stars with intrinsic variability because the surfaces of those stars are anyway moving because of the variability, and therefore we have Doppler shifts much larger than the wobble because of that. Okay, all right. So this is the radial velocity method. Now we move to the second method, planetary transits, and we shall come back to the radial velocity method again. But let's first look at the other major method, which is planetary transits. So what are transits? So transits are basically when a planet crosses in front of its parent star along the line of sight, it causes a tiny, very tiny, several parts per million decrease in the stellar brightness. Okay, this picture is from, perhaps you recognize this. This is a picture from the Venus transit of the sun. Here is the planet Venus transiting across the face of the sun. But so imagine this happening for a distant star. The difference is that you cannot resolve the stellar disk. So you cannot see this small dot here. Okay. All that you can see, because distant stars are so far away that they are, as you know, that they are basically like point objects in the sky. So you're looking at the whole star planet system together always. Okay. So you're looking at the total light only. You cannot resolve this spot on the star. But as the planet comes around and goes in front of the star, there's a very small dip in the stellar light. So we need to measure with ultra precise photometry these fluctuations in light, okay, of the star. So as the planet crosses the face of the star, it causes this dip. Okay, as it goes out, then again the starlight returns back to the original level. So this is what we measure, this dip. How big is this dip? This is several parts per million. How big is 1 part per million? So this is unimaginably small for us in light. So one can have some analogies. One analogy that is given is, suppose you are looking at a street lamp, let's say a sodium vapor lamp, or nowadays we have LED lamps on the streets. So we are looking at this bright street lamp from, let's say, something like 100 meters or 200 meters. Okay, and then you're measuring the total light of this street lamp through an instrument, and then a mosquito passes in front of the street lamp. The kind of dip that it causes in the total light is 1 part per million, and that is the sensitivity required of the instrument. And now, thanks to great technology, we do have such instruments. Not now, I mean, we have it for nearly now 15 or 20 years almost now, that we do have such instruments which can measure several parts per million fluctuations in light. Okay. So the occurrence of the detection of the transit depends on the alignment of the orbital plane and the line of sight, as you can easily imagine. If you're looking from the top, of course, you'll not see the transit. If you're looking face on, you have to look roughly edge on. And of course, the relative size of the star and the planet. If this planet is very small compared to the star, then this dip will be very small, and of course, it will be lost in the noise, right? So it depends on these factors. So this is again some real data from the Kepler telescope. You may have heard of the Kepler mission. We'll talk a little bit about that later. So let's say what we have here. So we have the average light from the star. Of course, the average light from the star also has tiny fluctuations, but let's say the average light of the star is given by this top red line. And then once in a while, this is there on the x-axis is time in days, you see these very sharp dips for a few hours. These are the planetary transits. Okay. Now look at the amount of the dip. It is about 2%. Okay, so this is very, very small dip. If you blow up any of these dips, you see something like this. So first of all, between these two dips, you get the time period. So in this is about 4.887 days. Okay, so that will give you the time period of the planetary orbit. And then each dip is actually this typical characteristic U-shaped curve. Okay, if you blow it up further, you can see that there's a transient phase here, which is called the ingress and the egress, and we shall see what they are. This is of the order of a few hours. And then there is a full transit, which is this bottom of the curve, which is again of the order of hours. And then you have again this pattern repeating after several days. Okay, so this is the typical transit light curve. So one has to analyze this data, and as we shall see, we can indeed learn a lot from this. Okay. So first of all, the orbital period can be obtained from the time between the transits, and immediately, as before, Kepler's law gives us the orbital radius. The features of the light curve, that is this U-shaped dip, these contain information about the relative size of the planet and the inclination of the orbit. How so? So typically, we have a characteristic U-shaped light curve. Now, first, let us consider, I'm focusing now on the left side of the slide. So let's consider the star as a uniform disk of uniform brightness, okay? Now, if we are looking exactly edge on, that is inclination angle of 90 degrees, then the planet would go across this diameter, right? But typically that is not the case. We always have some inclination and therefore the planet actually cuts through on a chord, right? As you saw in the Venus and the Sun photograph also, it cuts through a chord. So from this point where it is called first contact, and from up to here where the planet is fully inside the stellar disk, this is called the second contact, we have this transit phase, which is called the ingress. Okay, and then the planet transits across the face of the star. This is the full dip, and then again egress as it goes out of the star. So these are periods where we have partial overlap of the planet and the stellar disk. All right. So now, of course, real stars are not like uniform disks, disks of uniform brightness. There is a so-called limb darkening effect. I don't want to go too much into it, but basically what happens is that when you look at the central part of a stellar disk, this you can see even for the sun. If you look at the central part of the sun, it looks much brighter than when you look at the outer parts of the so-called limbs of the star. Okay, that is because the photons that you receive from this part come from a higher depth than from at the limbs, and photons at a higher depth have are brighter and have a higher energy, and so that's why you get a higher brightness here. Okay, so typical stellar disk is brightest at the center and dimmest at the limb, and there's a gradual darkening. This is called a limb darkening effect. Now, because of this limb darkening effect, as the planet transits, it does not block equal amounts of light, right? When it is near the central part of the star, it blocks the maximum amount of light because this is blocking the brightest part of the star. If it is the limb, it is blocking only the dimmest part of the star. Now, again, I remind you that you are not looking at this picture. What you are looking at is this whole integrated light of the entire stellar disk. Okay? So when the blocking is maximum, of course, you get the maximum dip. When the blocking is minimum, you get the minimum dip. And therefore, we have this characteristic U-shaped curve, because even during this, the brightness is not uniform as here, but rather graded. And that's what explains this U-shaped curve. Okay. So this is what a typical transit light curve looks like. We can get more information about this. So first of all, the transit depth, that is this maximum depth, this gives the ratio of the stellar and the planetary radius, because the brightness goes as the area, and therefore this dip gives you a ratio of the areas of the whole disk to that of the blocked disk, that is the planet. The duration of the ingress and the egress give you, one can measure the inclination of the orbit from this. Okay, I'll not go into the details of this, but the shape of this ingress and egress gives you the angle of inclination. And remember that the knowledge of inclination improves our estimate of planetary mass from the Wobble method. So if we look at the same star using planetary using transits and the Wobble, we can get the inclination from the transit method and use that in the Wobble method to refine our estimate of the mass. Okay. So one can have transits in multi-planet systems because, as we know now, that most planetary systems are actually multi-planet. So what happens? How do we deal with those? So what happens is that you get, of course, transits again. So this is again real data, and you look at, so you get dips with various periodicities and with various amounts. These are for various planets. Okay. So there are, in this system, actually, there are 7 planets going around the star, and you can analyze this data and actually differentiate between all these 7 planets. Okay, because the amount of dip is different for each planet, because the size of the planet will in general be different, and of course their orbits will be different. And if their orbits are different, then their periods will be different, right? By Kepler's law. So therefore, you can disentangle all this and get different orbital characteristics of the different planets. Now, sometimes, of course, the transits can overlap. right? So before that, first of all, one must understand that not all the planets may show transits, right? Only those planets which are aligned with your line of sight will show transits. There might be planets whose orbital planes are slightly inclined to your line of sight, and therefore you miss the transit. But for those which are showing the transits, sometimes the transits coincide, and then the light curve looks like this. Okay, let me again try to show you an animation to explain this better. Yeah. So there are two planets here. So now there are three. There's a big planet which causes a transit, and now the second planet is coming in. It causes another transit. Now the third planet. Now look, if I go back, sorry, I can go back a little bit. Yeah. So, oops. Yeah. So you see what happened here. So if you go back here, so now here there is only one transit happening, and now the second transit starts. So you get a bigger dip, right? And then before the second transit ends, the first transit ends, and the light goes up here, and then again and finally the second transit ends, and you get back to the overall thing. Okay, so this is that kind of light curve that you get in such cases. Okay, all right. So this is again real data actually from 2015. So there are actually 3 planets here. So this is 1C, 1F, and 1E. And as the transit the thing, so you get a complicated light curve, but you can analyze all this. Okay, you can identify, and there's a very good exercise actually to see which part is which transit. The deepest point is when all the 3 planets are in front of the star. That is the deepest point. Okay, and then one by one they go out, and you get back the original stellar luminosity. Okay? So this is how we detect multi-planet systems. Transits can tell you much more. So this is a look at the left side of the slide. So what we have at the top is basically again, all this is real data. So what we have is normalized flux from a star called HAT-P7. Don't worry about the name. Astronomers have habit of giving very strange names. So HAT-P7 is the name of the star. And then, so this first panel is ground-based data. Actually, this was taken from the ground. And sorry, I'm mistaken. This is already space data. This is from Kepler. So this is at magnification of 1. If you magnify this further, you get to see the stellar noise here, and you also begin to see a small dip here. And again, if you magnify it 100 times, you get the whole light curve like this. So you have this planetary transit here, and this, which you did not notice first here, there is a very small dip here. And there is a variation even in this light otherwise. Why is this happening? Okay. This is happening because as the planet goes around the star, so when the planet is in front of the star, so it is not reflecting any light from the star, right? And you get this primary transit. And then it goes out of transit, and it begins to reflect some part of its face of its lighted face is turned towards you. And so this is just like the phases of the moon. And then when it is just behind the planet, just about to go behind the star, behind the star, then it is almost like a full moon, and you get a higher brightness, okay, of that is the reflected light from the planet also reaches your eye. Again, remember that you are not looking at these individually, but you are looking at the total light from the planet and the star, okay? And that is what causes this variation, and then when it goes behind the planet, you get the star alone. So this level is a star alone light. So you get when the planet is hidden behind the star. When it is in front, you get this big dip. And when it is almost close, this is star plus planet. There's the maximum brightness. Okay. Now, apart from, so one thing is that it gives you, so therefore this secondary transit gives you actually a measure of the stellar brightness alone. Okay. Now looking at the secondary and the primary transit, or rather the light just before the secondary transit and the light just before the primary transit, what we get is reflectivity or albedo of the planet. Okay. Because we know that this extra light is coming from the planet. And this reflectivity tells you a lot about the composition of the planet. So this is how, this is one of the clues to know what the planet is made of. What's there on its surface? What kind of albedo or reflectivity does it have? Okay. One can do more. So when the planet, when the transits the star, it's coming in front of the star. So now, if the planet has an atmosphere, then the starlight from behind the planet is coming into your eyes through the planet's atmosphere, right? And that therefore gives you some clue about the planet's atmosphere. Now, if you look at different wavelengths, first of all, because the planet's atmosphere absorbs light at different wavelengths differently, the dip in the transit will be different for different wavelengths of light. Even the shape of the light curve will be different because of the absorption in the planetary atmosphere. Okay. On top of that, now if you look at the right side of the slide, so on top of that, as the starlight is coming, suppose this is a spectral line that is there already in the star. Okay, so let's say this is an iron line, or this is a silicon line in the star. There's an absorption line, you get an absorption profile. And then a transit happens with the planet with its atmosphere. Now this light passes through the planet's atmosphere. And if there is iron also in the planet's atmosphere, then you get a higher dip. This increased dip is because of what is there in the planet's atmosphere. So this is how we get clues about the composition of the planet's atmosphere. Now, this is another clue that we can get. So sometimes, and this is again real data, sometimes we see such light curves. That is, there is a transit which is a regular U-shaped curve, and then there is a spike in that. Why is that? That is because if the star has a star spot, you are familiar with sunspots, I believe. So if the star has a star spot, and then this gray band is a path of the planet across it. When the planet overlaps with this spot, then of course it is covering the same part of the star. So it's not blocking anything extra. Therefore, the amount of dimming will go down actually, and the brightness will increase when the planet overlaps. Because without the overlap, both the light of this whole disk is diminished both due to the spot, which you don't know, of course, and the planet. But when the planet covers up this spot, then there's actually an increase in the brightness. So you can detect existence of spots on a star. Not only that, now look at this. This happens not on every transit, for example, for this data. This happens on transit number 217, transit number 223, 229, 235. So every 6th transit this is happening. So that is because the star is rotating, and this spot keeps coming back again and again. In between, the planet has crossed it 5 times, but the spot was not there on the face of the planet, right? So by looking at this, now we know that the stellar rotation period is 6 times that of the transit period, which we have already obtained. So now I know how fast the star rotates by marking this indicating spot on the face. Okay, so we can get, as I said earlier, that learning about planets also helps us learn about the stars. So this is an example of that. So we know if the star is active, if it has many spots on its face, and what is the stellar rotation period, because I can now measure it. The size of the star spot can also be estimated from how big this peak is, if it is, because we can characterize the planet, and therefore with the relative size of the planet on the spot, I can get the size of the star spot as well. Okay, so if we put together our knowledge about the Wobble and the transit together, then we can learn a lot about the star-planet system. So first of all, the period, either from the wobble or the transit, gives us the orbit size through Kepler's law. The transit depth gives us the planet size. Of course, we have to know the size of the host star. We have to measure the radius of the host star independently. There are methods to do this. The duration of the ingress and the egress give us the inclination of the planet orbit. The inclination now improves the mass of the planet. This is where the two methods come together. The inclination can now improve the estimate of the mass of the planet obtained from the wobble. Again, we need to know the mass of the host star. The size and the mass of these gives us the mean density of the planet. If we know the mean density, that is a clue to its composition, because now we can say whether the planet is a rocky planet or whether it's a gas giant, whether it's like the Earth or whether it's like Jupiter. Okay. The spectra during the transit, which I just described, provides clues about the planet's atmosphere. The secondary eclipse gives us the reflectivity of the planet's surface. So all these help us to characterize the planet. And the orbit size with the host star temperature, again, the host star temperature can be measured independently. And if we know the orbit size, then we know what will be the temperature on the, roughly what will be the temperature on the surface of the planet, and therefore whether it will be habitable or not. We shall come to that question later. Okay, now it may appear that, I mean, how can we distinguish a planet transit from other variations on the star? Because after all, there are spots on the star, as we just said, and stars also have intrinsic variability. They have pulsations. And how do we know whether it's a transit or it's a pulsation or a star spot? The clue is the different time scales. Okay, they don't happen on the same time scale. So if you look at the graph on the left here, so this is again real data. So on the x-axis is the time and the y-axis is the relative flux. And this is the light curve of the star. So what you see are three kinds of variation here. One is very clearly this sharp hill and valley kind of variation. This is actually due to oscillations of the star. Okay, they happen on a time scale. If you look at this x-axis, they happen on a time scale of about 5 days, 4 to 5 days. These are oscillations in the star. These sharp dips that you see here, these are the planetary transits because they take a few hours. Okay, so this is very distinct from the oscillations. And you will notice that there's an overall modulation of this entire thing. That is because there are spots on the surface, and this modulation period is linked to the stellar rotation period. So this modulates the total stellar luminosity, because whether the spot is on the front side of the star or whether it has gone behind will determine its average luminosity. And therefore, this modulation period is the stellar rotation period. So these things are on different time scales. It is not always known. In this particular example, the oscillation period is much smaller, much larger than the transit period. That may not be the case always if you look at the graph on the right side. So here, the transit period, you can see this is now in hours. The x-axis is in hours. This is, of course, for a different star. So you can see that the transit period is about 7 hours or so. And here you see that these are the oscillation periods, this tiny bits from here. And they have much smaller periodicity. Okay. So in any case, there are differences in time scales. Of course, if the oscillation period and the transit period are of similar periods, then we have a problem, and we may have difficulties in disentangling them. Although the transits have very telltale shape of the light curve, which the oscillations also have something, again, some characteristic shape, but not like this U shape. Okay. So that is the kind of thing that we're talking about. All right. What is the probability of transits? What is how probable it is that we'll see a transit? Now, as we said earlier, that you have to look at the star-planet system almost edge-on. Okay, how much variation can we allow? So, if this is the star, and so this D star is the diameter of the star, and this capital D is the diameter of the planetary orbit. So you can see that this angle has to be D star by D by 2. And if you rotate it by 2 pi in this direction, you get a solid angle and you have 4 pi d by d, 4 pi d star by d, and the geometric transit probability is therefore d star by d. So d star is the stellar diameter, capital D is the planetary orbital diameter. So the transit probability depends on the size and the orientation of the orbit. Of course, if you are looking at from a different angle where this is more face on, you will not see the transit at all. But even if you see it, so this geometric transit probability is about 10% for very close planets, and for true Earth analogs, like that is for an Earth-like planet at about 1 AU distance from the star, this is about 0.5% is the probability of observing the transit. So the question is, can we observe transits from the ground? So as I said, the relative change in the brightness is equal to the ratio of the areas. So this is, for example, if Jupiter would transit across the face of the sun, it would look something like this. Notice that from far away, it does not matter how close Jupiter is to the star, because the distance between the Jupiter and the sun would be much, much smaller than the distance from which a distant observer will be looking at the sun. Okay, so it is almost like pasted on the face of the sun. Whereas if it is the Earth, this covers a much smaller area, and therefore we need to measure about 0.01% fluctuation in light. The transits are short-lived, so we don't know if a planet, if we knew, I mean, our problem is solved, that if a planet, if a star has a planet, so we have to, and then the transit happens quickly over several hours. So we must be looking at the right star at the right time. Now, how do we do this? We don't know, I mean, which planet has, which star has planet and when the transit will occur. So the solution is to look at a large number of stars all the time or for a long time. Okay. So you look at many stars for a long time. That's how you detect. And then you expect that some of those will have planets, and out of those planets, some of them will transit during the time that you're looking at them. So this can only be done in survey modes. Now, because of the difficulty in measuring this light very precisely, we talked about several parts per million earlier. So necessarily such observations have to be done from space. We have to go above the atmosphere, because the atmospheric twinkling is a much bigger effect than the transit dip that you will get. Okay. So this can be done from space, and from space, what you need to do is to point your space telescope to one part of the sky and keep looking at it for a long time. So the NASA Kepler mission was a mission of this kind. So this was one of the most successful missions of space missions ever launched. This was launched in 2009 with an expected lifetime of 3 years, but it ran for 9 years till 2018. So this was a 1 meter telescope with a field of view of about 100 degrees square. And it looked at one patch of the sky here near the Cygnus constellation continuously and simultaneously, and monitored 170,000 stars for 3.5 years in the first part of its mission. Okay. So it just looked at one patch of the sky, and it found many transits. The successor to the NASA mission is the currently running test mission of the Transiting Exoplanet Survey Satellite. This is a slightly different profile. This was launched in 2018. This is also a NASA mission. This is optimized for finding terrestrial planets, for small planets. It observes the sky for anything between 27 days to nearly a year, but it will cover the whole sky over its entire mission. Okay, so this is the mission that is running right now. Okay, so I have come to the end of the transit method. Now let me just check the time. Yeah, I think I will skip these other methods and I will only answer them if there are questions. Let me quickly go over to the question about extraterrestrial life. So the question is, are we alone in the universe? So first of all, for life to exist, we expect the planet to be in a so-called habitable zone. What is a habitable zone? This is a range of orbital distances where the temperature will be conducive to life. Now, when we talk of life and when we talk about habitability, I must say right at the beginning that we are talking of life as we know it on Earth. There might be other kinds of life possible which do not require let's say, oxygen, or which do not, well, oxygen is not strictly required for all life, which do not require water. Now, that is some kind of life that we don't know about, so we can always speculate about it, but there's no point in worrying too much about it at this point. So what we are talking about here is life as we know on Earth. So for that, we think that water is essential. So we need to have water, liquid water, on the surface of the planet. So therefore, the planet must be at such a distance from the star that it has liquid water on its surface. Now, remember that this depends not only on the distance from on the star, but also what kind of star it is orbiting. So for a hotter star, this habitable zone, this green band, is further away, right? And for a cooler star, it is close by. For a sun-like star, you can see here that roughly Earth and Mars is roughly at the inside the habitable zone. Okay, so the other factor that will determine whether there is liquid water is atmospheric pressure. So when we talk of water, we talk of pressure. If there is sufficient, water if there is sufficient pressure of the atmosphere on the surface of the planet. So what are the conditions of life? So we can summarize them as follows. So existence of life, again, as we know it, needs, first of all, a rocky planet, because we don't think that life can exist on a gaseous planet like Jupiter, because we need water. So it's a rocky planet with an atmosphere, which is not too large or not too small, which I'll talk about the atmosphere in a minute. We need the right kind of temperature to sustain liquid water. And we also need the atmosphere to be of the right composition. Now, the temperature depends on the temperature of the star, distance from the star, the reflectivity of the planet's surface, the shape of the orbit, eccentricity. This is an important thing. If the orbit of the planet is highly eccentric or highly elliptical, that is, so what will happen is that it will have wild fluctuations of temperature when it goes far away from the star and comes close to the star, and therefore the temperature will not be stable, and that may not be conducive to life. And then the temperature also depends on what is there in the planet's atmosphere. There's the composition of the planet's atmosphere. So the atmosphere is, the composition of the atmosphere must be such that it has a mix of life-supporting gases. For example, oxygen, there might be other life-supporting gases also, and mostly inert gases. There cannot be too much of oxygen, then everything will burn up. So the atmosphere must be mostly inert gases, like we have on the Earth, for example, nitrogen. We need to have stability of temperature, so we need to have greenhouse gases as well. So not all greenhouse gases are bad, so we need to have some amount of things like carbon dioxide, which will keep the heat in, because otherwise during the nighttime, the surface of the planet will be too cold, right? So to retain the heat, we need greenhouse gases. The atmosphere must be a protective shield against the cosmic rays, UV rays, meteoroids. This is very important. This is what protects us from all that, all these things that come in our way. The meteoroids burn up in the atmosphere, and the cosmic rays and the UV rays are absorbed mostly in the atmosphere. The other role that the atmosphere must play is through transport of water through rain. Now, this is strictly needed for life to exist on land. So you need to transport the water in the oceans onto land, and that can happen only through the atmosphere, through rain. So these are this is a sort of a brief summary of what are the conditions of life that we are looking at. Okay. So what kind of planets have we observed, and how do they compare to this? So the nearest Earth-like planet is in Proxima Centauri. Its scientific name is Alpha Centauri C. So Alpha Centauri B, B is for the planet. This is about 1.34 parsecs from the Earth. The host star is about 1/10 of the mass of the Sun. The planet is about 30% heavier than the Earth, but the orbital radius is much, much smaller. Okay, so the planet is in a much tighter orbit. Okay. And I think there's somebody scribbling on the screen here. So, and then it is characterized to be a rocky planet, but it is also tidally locked, which means that there'll be extreme temperatures on the surface of this planet, which will be unsuitable for life. Okay, let me go ahead. So this is a multi-planet system. This is a planetary system, much like our solar system in some ways. This is called TRAPPIST-1. This is about 12 parsecs from the Earth. There are at least 7 planets that have been detected around a 0.08 solar mass star. So the star is much smaller than that of our sun. The initial discovery was made by this telescope, from which it gains its name, TRAPPIST, Transiting Planets and Planetesimal Small Telescope. And the Himalayan Chandra Telescope in Hanle, India, was also involved in characterizing these planets later with additional data. And then more planets were discovered by all these telescopes. The planet masses are between 0.4 to 1.4 Earth masses. The orbital distances, you will notice, all of them are much smaller than the orbital distance of the Earth from the Sun. So the temperatures are between that of Mercury and Mars, and all planets have rocky composition. So this, notice that even though the planets are much closer to the star, the temperatures are not that high because the star is a smaller star than of the Sun, and therefore a cooler star. All the planets have rocky composition. So again, one could have hoped for existence of life on these planets, at least some of them, but recent studies have revealed that TRAPPIST-1 ejects very strong flares. It's a very active star. And therefore, the flares are much stronger than what are ejected by our Sun. And therefore, most likely, they will obliterate the possibility of any life on any of the planets. The planets are unlikely to have atmospheres which are strong enough to prevent these flares from reaching their surfaces. So the exoplanets, so this is the summary of the exoplanets that have been detected so far. So this is with the year of discovery, and these different colors are for the different methods. So we have discussed only these 2 first methods. The red one is the radial velocity method, and the green one are the transits. As you see that most of the discoveries are through these methods, and then there are these other methods also mentioned here. And you notice that there are some spikes here. That is because of a fundamental change in the way the data is analyzed. So we learned to analyze the data much better through some new algorithms in these years, and therefore the number of planets detected shot up. And nowadays, as you can see, that most of the detections are dominated by the transit method. Most of this is contributed by Kepler and some by some other missions as well. So this is a cumulative graph. So now we are above 4,000 planets that have been discovered so far. So as of today, number of confirmed planets are 4,171. And there are another more than 5,000 planet candidates. Now these candidates are planets where are situations where we think that it may be a planet, but when a planet is, nowadays all planet discoveries are confirmed through both the transit and the radial velocity method. So if a transit is observed, then you know which star it is. So now you can point your telescope and observe the star spectrum and see if there is a wobble there, and measure that wobble and match it with the transit measurements, and therefore confirm the planet. So it takes some time. So that's why there are about 5,000 planet candidates. Many of these will be confirmed, hopefully, in the next few years. And very large number of stellar stars have planetary systems, just like our solar system, more than 3,000 of them. If we characterize the planets, so on this graph, you can see here, the yellow dots here are the planets which are discovered through the transit method. The x-axis is the orbital period in Earth days. So this is the Earth's period will be somewhere here, 365 days. On the y-axis is the planet's mass in terms of Earth masses. So the Earth mass will be here. So as you can see that the radial velocity detections, which are the blue ones, are mostly for large masses, okay, as we said earlier. And the initial discoveries were in this range where the orbital period and therefore the distance from the star was small. But nowadays, with improved sensitivity, we can also detect large planets away from the star. And these yellow ones are all the transit detections, which can detect much smaller planets in orbits in a range from small to large. Okay, So if we look at the census, they're almost equally distributed between gas giants like Jupiter, then Neptune-like planets. Then there are super Earths, which are slightly bigger than the Earth, and terrestrial planets are smaller in number. So if I again look at this graph, so this is the Earth, will be on this graph. So the planets that we have observed are the hot Jupiters are here. These are massive planets in tight orbits. These are the colder gas giants. These are also big planets, but far away from the star and therefore colder. Then we have the ocean worlds of the ice giants. These are also big planets, but at smaller temperatures. Then we have the lava worlds. These are the small planets very close to the star. So these will be very hot and active. And then these are the rocky planets that we are looking for mostly for existence of life. As you can see that this part has not yet been populated simply because it is harder to detect these in either method. These are small planets and these are harder to detect. So here on the x-axis is the mass in Earth masses. On the y-axis is the radius. So now we are comparing the mass and the size of planets. So these are all the planets that are detected. The Earth is somewhere here. So these curves are for densities. Okay. So this one is if the planet is a completely water or ice planet. Okay. So that will be this line. If it is completely made up of iron, then this will be that, and something in between here. The Earth is somewhere here because it's mostly water. And then, but as you can see that there are very few planets which are in this domain. Okay, most of the planets have different densities. Here we compare the size of planets with their equilibrium temperatures. Again, the Earth is here at about nearly 300 Kelvin at 1 Earth radius. And as you can see that there are very few planets which have been detected which are similar to the Earth, but we are getting there slowly. Okay, so what are the best candidates for life as of now? So several have been identified, though I must say that none have been, we cannot say for sure for any of them that there will be life, or even we cannot say whether all the conditions are satisfied for life. Okay, so but they are in the habitable zone. They are rocky planets, and their expected surface temperatures are thought to be favorable to have water on their surface. Okay, in some form, maybe ice, maybe liquid water. But there are many other factors. There are, in some cases, for example, you can see the TRAPPIST-1 planets here. Now, recently, we think that these cannot harbor life simply because the host star is too active. So it throws huge flares at these planets, and that might kill life. So existence of life depends on many factors. So, and there's been no planet so far where all these have been found to be favorable, or even known what the factors are. Okay, so let me summarize. So we talked about two methods. The radial velocity method, this can be done from the ground, and this provides orbital radius and mass of the planet. But large surveys are difficult with this because spectrographs, it's difficult to do large surveys with spectrographs because it takes time to obtain spectra. The transit method for these space observations are most efficient, and there have been a couple of very successful space missions. These provide the size and density of the planet. These reveal information about planetary atmosphere, and these have detected many planets through large surveys. So what are the takeaway points? So the hot Jupiters are easiest to detect, that is large planets in close orbit. These are easiest to detect in either method because they are large. Okay, primarily because they're large, and because if they're close to the star, they're easy to detect through the Wobble method. But given the fact that we have discovered almost equal amounts of lower mass planets and even smaller planets, tells us that smaller planets closer to Earth size are more common because this selection bias is overcome for them, right? Because we have detected almost equal numbers of them. So we think that now most stars have actually smaller planets. These are more common than large hot Jupiters. 90% of solar type stars are planets, and most have multiple planetary systems. Okay, metal rich stars, let's not get into this. Basically, stars which have higher abundance of the heavier elements, these are more likely to harbor planetary systems. Our sun is one such star. Planetary migration and eccentric orbits, that is where the planets change their orbits. So planets which are at a certain point of time, which are closer to the star, move away and go to further orbits and vice versa. These things are very common in other stars. So in that sense, the solar system is an exception because this has not happened much we don't find much evidence of this in the solar system. So far, more than 4,000 planets have been detected and around 5,000 candidates are waiting. And the first detections of Earth-like planets in the habitable zone have been made, although no definitive statement can be made about the conditions for life to be favorable. Okay, I think I'll stop here. Thank you. Thank you to all of you, and I can take some questions.
Yeah.
Yes, sir.
Yes.
Yeah, thank you, sir. Shall we start the question session?
Sure. Yeah.
So here are some questions from Zoom as well as YouTube. I will go one by one.
Yeah.
Okay, the first question, that is, which type of telescope exoplanets are detected?
Yeah. Okay. So first of all, these are all optical telescopes because we are looking at stars, and stellar light is brightest in the optical range. Of course, stars also emit in ultraviolet and infrared and radio, but in the optical range, that is in the visible range, the brightness is most, and therefore when we look at stars, remember again, whenever we are detecting exoplanets, we are looking at starlight, either in all the methods. Okay, so these are all optical telescopes. You don't really need very big telescopes. So for the transits, more important is that you go above the atmosphere, that is, you go to space. Otherwise, the twinkling will kill the transit effect. And as you saw for Kepler, it's about a 1 meter diameter telescope. So you don't need a very large telescope for this. For the other methods also, for the radial velocity methods, the best spectrographs are put, some of them are on large telescopes like 4 meter class telescopes, but many of them are on smaller 2 meter class telescopes. So these are the kind of telescopes that are used.
So next question.
Yes.
Is it possible to predict exoplanet on the basis of mathematical calculation?
No. I mean, you can have a theory and predict, but there is no value to that really, because what we have to do is that we have to detect. So the numbers that are there on this slide here, sorry, just minimize this for a moment. So the numbers that we have here, when I say that 90% of solar type stars are planets, how do we know this? This is from statistical analysis. So we look at many solar type stars and we see how many of them have planets, and we find that 90% of them have planets. So you can use statistics to predict the number of planets. There is no theory which says that there will be so many planets around 6 stars.
So next question. How do we know about atmosphere of planet during transit?
Okay, so this I explained earlier. So let me go back to this slide again. Yeah. So one thing is that from the secondary eclipse or the secondary transit, we can get the idea of the reflectivity of the albedo of the planet, as you saw here in this graph, for example.
Anwesh,
so
you got to share the slides again.
Oh, sorry. Yes. The sharing has been stopped. Just a minute.
Yes, sir.
Can you see the screen now?
Yeah.
So first of all, you can get the albedo or the reflectivity of the planet by comparing that how much increase in the brightness is there close to the secondary eclipse. That is this part. So that is one thing. The other is that through transmission spectroscopy. So during the transit, the planet is passing in front of the star, right? So now the starlight comes to you filtered through the planet's atmosphere. So you are lighting up the planet's atmosphere with the starlight and looking at that light. So by looking at the spectrum during the transit and comparing it with the spectrum outside the transit, the difference is what is there in the planetary atmosphere. That's how you get information about the atmosphere of the planet. The other part is that you also get different dips and different shapes of the light curve at different wavelengths. This is because of the planet's atmosphere. What is in the planet's atmosphere will determine how much light is blocked. And I mean, rather, what is at each frequency, how much light is blocked, right? So the frequency dependence of the amount of light blocked will give you a clue about the planet's atmosphere. So these are the ways in which we can study the planet's atmosphere.
Okay. So next question. Yeah, how do we detect orbiting planets having a very large time period? Probability of planet-star system appearing in the line of view will be very small.
Correct. Yes. So indeed, this is a problem. So unless you come back, you observe long enough to observe several transits or several Wobble periods, you cannot do this, right? So, for example, the Kepler mission did observe a certain part of the sky continuously for 3.5 years, right? So a planet which has a period of close to 2 years would have 2 transits in that period, right? Planet close to about with a period of about 1 year would have about 3 transits. So you have to of course watch the planet continuously or at least repeatedly. The test mission, for example, will re-observe parts of the sky that it has observed earlier, and then compare that data with the earlier data and try to get periods of planets which are very long periods, okay, by coming back to them. So that's the only way to do it. One transit is not enough evidence of a planet because there is noise in every data and you can never be sure. And plus, of course, you cannot get the orbital period.
Okay, sir, next question.
Yes.
Though not detected yet, what if 2 planets lies diametrically opposite in an orbit? Or if we are observing something like Trojan asteroid as in Jupiter's orbit, how can we discern these systems?
Okay, so let me answer the second part first. So the detection of an asteroid is extremely unlikely in the present case because of the very small size of this. Okay, recently some detections of moons around exoplanets have been made. Looking at the data, if you have very good quality data where you can observe secondary features in the transit light curves, you can, so by looking at small kinks in the light curve, you can detect the presence of moons. But that is again because it is periodic in nature, and therefore you can be sure that it is a real signal. An asteroid or something, the likelihood of periodicity within a short time is very small, and therefore that would be very hard to detect. And of course, it is extremely small, much smaller than the moon, so its signature will be completely lost in the data. Okay. The first part, sorry, what was the first part of the question? Can you please repeat the question?
First part, that is, yeah. Though not detected yet, what if?
Yeah. So this is of course a very hypothetical question. That 2 planets diametrically opposite in the same orbit. In nature, this almost never happens, and it's very unlikely that will happen because, but of course one cannot rule that out, or at least very close orbits which are just out of phase. In that case, there is no easy way to do that. I mean, what you will get is basically you will think that the planet has half the period, but then if you look at the Wobble method, you will run into inconsistencies, right? Because there won't be any Wobble if it is a perfectly symmetric case.
Okay. Yes, sir. Next question.
Yes.
Can you also throw some light on the recent exoplanet discovered called KOI 45604 orbiting Kepler 160?
Yeah. So this is So KOI is, for your information, is Kepler object of interest. So Kepler stars which have planets which are particularly interesting are just renamed KOI. Okay. So no, about this particular thing, I don't have the data or any particular information at present, but there have been several such things detected. You will find some of these in here, in this. So I mean, here they are. See here, Kepler 1229b, Kepler 442b. So out of this, for example, I can tell you that 442b and 186f or 62f, these three are considered very strong candidates for habitability. But and so the particular case that you are mentioning will be something similar to this. So there are, every once in a while you will read newspaper reports that such and such planet has been detected, which has such and such characteristics. They are exciting, yes, but there are several of them which have been detected earlier also. Some of them, so they will typically be interesting in one way or the other. Either they will be almost Earth twins, that is, they will have almost the same kind of mass as the Earth, or sometimes they will be at almost the same orbital radius as the star, around the star, very similar to the sun, and therefore the temperature is expected to be very close to the Earth. But then the other information is simply not available usually. That is, we know very little about their atmospheres yet. We know very little about what the star is doing, whether the star is very active, and such things. So that's the thing. About your particular whatever KOI object, there are plenty of KOI objects, KOI stars. Many of the, I mean, most of these are actually have some KOI number also. So no, I don't have any specific information on that.
Okay, so next question.
Yes.
Also from the mass of planet, how can we identify the type of planet or estimate its density?
Size of the planet?
Also from a mass of planet, how can we identify the type of planet?
Oh yeah. So no. So you cannot get, of course. Yeah, very good question. So the point is that so you have to look at this slide here. Just let me get back to that. See, the transit depth will give you the planet size. Okay. So because that will, if you know the radius of the host star, because all you get is a ratio of the radius of the planet to the star. So there are other ways to estimate the radius of the star very precisely, namely with using stellar oscillations, which happens to be my own area of research. So once you know the radius of the star, then you can get a good estimate of the radius of the planet. Now, the mass of the planet you can get from the Wobble method, okay? Provided you know the inclination. The inclination you can get again from the transit. So you have to put together all this information, okay? The mass of the planet is, again, you get a ratio of the mass of the planet and the star, but again, there are other methods to estimate the mass of the host star, and therefore you can get the mass of the planet. So these two are independent pieces of information, the mass of the planet and the radius of the planet. Once you get those, then you can get a mean density, and then you can say whether it's a rocky planet or a gaseous planet.
The next question.
One does not follow from the other. There are two pieces of observation. One is the Wobble, the other is the transit.
Okay, so next question.
Yes.
How long it takes to discover an exoplanet?
So it depends on how lucky you are. So of course the planet has to either transit the star, or if you are able to measure the Wobble, then the period of the planet needs to be shorter than your observation period. So for example, if you look at this Nobel Prize discovery, which was in 1995, so they observed a planet which has a period of 4.5 days, right? That's because they were looking only for maybe a month or so, right? And then there were many periods which they could cover in this time span, and therefore such a planet could be discovered. Now, let's say if you're observing for 1 month, you cannot hope to observe a planet with a period of 2 months or even 20 days, right? So depends on what kind of planet is in your line of sight and how long you're observing. For transits, as I said, the Kepler mission, for example, which is responsible for more than 3,000 exoplanet discoveries, but you had to point the Kepler telescope for 3.5 years in the same patch of the sky. So one has to be very patient. So Kepler observed 170,000 stars continuously for 3.5 years, and we have about 3,000 confirmed exoplanet detection. Some more may come in the following year, so maybe that 3,000 will go to 5,000, but that's all.
Sir, next question.
Yes.
Yeah. Can you please comment about technological advance in CCD array based detection of exoplanets from Kepler to TESS mission? What is the role played by AI machine learning?
Okay, so first of all, I'm not an expert in any of these, either CCD technology or AI. But one thing I know is that they're not the same thing. So if you're talking of CCD and AI, these two things are completely different. So first of all, about CCD, so as I said, I'm not an observer, I'm not an expert at all in such matters. But all I can say is that the sensitivity of these CCDs was extremely high. And these are, so you can see here the CCD array here in this, here. So, and in these 3.5 years of mission, about, I think 4 or 5 of these 42, I think there are total 42 CCDs here. 42 were lost. The remaining things work perfectly fine. I can't tell you the specifications of these CCDs, but you can look up the Kepler website, very easy. You just Google Kepler and you get immediately into the Kepler website, where you can get all these details, and also for the test mission, what kind of CCDs they are, etc. I cannot tell you that. About AI, that is relevant for the analysis method, right? So indeed, there are many automated methods, and there is deep learning and machine learning and all the neural networks. All such things are employed in the detection of exoplanets mainly from transit data, because there is, as you can imagine, there is enormous amount of data. If you look at 170,000 stars continuously for 3.5 years, is a huge amount of data that you generate, right? So you have to crawl through that data and look for transits. And this is indeed and then identify patterns. Right now, these things are certainly done very well through these modern techniques, and they are being done. However, I must also say that many exoplanets have actually been detected after all these pipelines have been employed on the Kepler data, and then these data was given to the general public and to students and other interested people to actually manually look through the data and try to find patterns. And many exoplanets have been detected in that fashion, which just shows that the human brain is perhaps equally, if not better, equally good, if not better, at identifying patterns, which all these algorithms had missed, and then somebody looking at it manually found.
So next question.
Yes.
How to detect magnetic field on exoplanets?
That would be very difficult. You can detect only through transmission spectroscopy by looking at the shift of spectral lines, but that is the effect will be much smaller, because you don't expect a planet to have a huge magnetic field. And secondly, to begin with, you don't know which are the correct lines in the planetary atmosphere. That itself you get by comparing with your lab data, and therefore to detect shifts in them. I don't think currently the technology is at that level where we can do this.
That's the next question.
Yes.
Can the star spots be identified uniquely based on rotation period and their transit date? And another question also. Star spots can be identified uniquely. Okay. And what's the other question? How can we differentiate between star spots and smaller transiting planets having similar insights?
Having similar?
Insights.
Size.
Size.
Oh. As I said, it's all in the point is not in the size. The point is in the time scale. Okay, if you look at this graph, the star spot variation here is this big modulation, which is a period of, if you look at this graph, let's say from here to here, so this is about 100 days, right? Because you're looking at a pattern, let's say half a period somewhere from here to here. So whereas the transit happens over several hours, so you're talking of days. So no star spins on with apart from pulsars, no stars spin on time scales of hours, right? So stars are not such fast rotators. Typical stars, so the sun, for example, spins once in about a month. Other faster rotators are there, but which typically take days. The transit time scale is of the order of hours. So there is no confusion between the stellar rotation effects and the transit effects in terms of time scale. In terms of the size of the spots, those will give you, if the size of the, sorry, I'm putting the slide here, just let me, yeah. So if you have a size of the spot as large as the exoplanets, then you will have this peak go all the way up here. That's the kind of things that you will have. Okay. Was there another part of the question? I forget.
Wait,
yeah. How can we identify? No, we cannot. Yeah. We cannot identify spots. Well, no, we cannot, because I mean everything. I mean you don't know exactly, and neither is it useful. It does not have any to know whether the spot is on the right side of the star or on the left side. It may, if you are looking at a star of the star at a given latitude is not of much use, because with the rotation it will change. So there is no way to do this, because you are not you cannot know exactly where the planet is transiting the stellar phase, right? You don't know the latitude of that. There's indication, but then there's a degeneracy of 2 in that. It can be either in the northern or in the southern face of the hemisphere of the star.
So next question.
Yes.
Is planet always exist or having any lifetime? No. So this is something that relates to the theory of planet formation, and this is something that we have not discussed today. There are several models of planet formation. There are several models of how the solar system came into being. The first thing I must say is that our models regarding the formation of the solar system itself have to be revised now in the light of what we are seeing in other stars, where we see a lot more planetary migration and a lot more eccentricity, which we do not see in the solar system. So our solar system is quite an exception in that sense. So typically planets are thought to be formed from the same material, from the same disk from which the star is formed. It is called the protoplanetary disk, and so they are typically thought to be almost as old as star. Now in astronomy we talk of ages and times. Almost may mean a few million years or even tens of millions of years here and there. But typically we think that the planets are formed at least soon after the star is formed or simultaneously with it. How long a star will survive depends on many other factors. The star can be knocked out by some collision or something. If it is too close to the planet, to the star, with the star fusion, may get bigger and swallow the planet. If it is too far away from the planet, it may slowly drift away from the star and not remain a planet any longer. And such things from the and such things. So say planet will live. Typically, as long as a star is in its so-called main sequence phase of evolution, that is about 90% of its lifetime, when it is burning hydrogen into helium only, planet is expected to survive
that path, but it cannot be said definitively for distant planets. Yes.
So next question. Hello.
Yeah, you can go ahead.
Okay. Is it possible to measure the
Yes.
gravitational force of exoplanet?
On whom? On the star? That's what you're measuring in the Wobble method.
No, it's a question
You're
like,
measuring actual gravitational force.
yeah, gravitational force.
Yeah. The wobble happens because of the gravitational force of the planet on the star. So in the method that if you think in the gravitational anything, next question? Is there anything else?
Question. Yeah. So next question. It would be very interesting to know about efforts in understanding the atmosphere of the closest exoplanet. And that is just a comment. Next question. Do gravitational lensing affect the observations? Can we explore the exoplanet using astronomy beyond optical region of EM?
Yes. Yeah. Optical. Sorry, I think there are mixed questions. So first, let me answer about the gravitational lensing part, which I did not have time to go through. Yes, indeed, there is a method based on gravitational microlensing. So so the situation is like this: that suppose you have a source star here, and then you have a lens star in front of it. This is the observer, and so what you are looking at is the light of the source star, okay? And then the lens star crosses in front of you between the source star and the observer, and you observe a gravitational microlensing, right? So, so the gravitational, so this I'm not explaining. I hope the person who has asked the question knows already what is gravitational lensing. So the point is, as the lens star crosses in front, that you get a microlensing event. You can see here that, so this is, you're looking at the light of the source star, okay? So you see a brightness. Now, if there is a planet which is going around the lens star, which means that now the mass distribution of this system has a time variation, right? So when that happens, when there is an alignment of this planet also with this, you get a one-time spike in the light, which is like here, okay? Because the planet is also aligned at that point, along with the lens star. And this way, some planets have indeed been detected. But this can detect small planets in wide orbits because of the, because lensing allows that. But this is, of course, a highly improbable alignment. So this is a chance effect. I mean, if one detects certain things like this, it can be interpreted as a planet observation. But one cannot plan observations hoping for microlensing events because these are highly improbable alignments, right? So this is not a method which can be used as a survey mode or as a confirmation of exoplanets. And this is certainly non-repeatable because the next time the planet comes around, the lens star would have moved. So this whole, so it's not possible to determine the period of the planet.
Next question.
Next question.
Yeah.
Yes.
What is the distance limit of exoplanet detection with existing method?
What is the what?
Distance limit for exoplanet detection with existing method.
Okay, so the distance limit is essentially set by how bright the star is, because you need good signal to noise ratio in both these methods, both transits and the Wobble method. If the star is too far away and its light is too faint, then the noise in the data will not allow you to make these ultra precise measurements of these tiny fluctuations, either in the Wobble or in the transit. So that is typically what sets the limit. And so that of course depends on what kind of star you are looking at. If the star is bright, it can afford to be at a slightly larger distance. If it is a dimmer star, then it needs to be at a smaller distance. The exoplanets that have been detected so far, if I remember correctly, I think the farthest ones are only a couple of 100 light years away, or maybe slightly more, not more than that. And the closest one is about 4 light years away.
So next question related to this only.
Yes.
Is it possible to measure the density of the exoplanet, which is almost millions of light years away from the Earth?
Millions of light years away from the Earth, we won't detect the exoplanets. Sorry. So that's a completely hypothetical question.
Okay,
Doesn't make any sense. Because millions, as I just said, I mean, we can only detect only up to maybe hundreds of light years. Yes.
So next question.
Yes.
What is center of mass of the universe is located?
Where is the
There
center?
is no center of mass of. There is no center of mass of the universe, and this question is completely out of topic of this. We can have a whole lecture on that, but there is no center of mass of the universe.
Next question.
So I'll on this question. Yes. Yes.
Yeah. It is
But
about,
if you're interested, you can read up this. Just a minute. If the person is interested, he or she may read it up on the internet. There are plenty of sites which explain why there is no center of mass of the universe. Yes.
yes, sir. Is there only HE formation from H2 in any stars or other?
Is there only? Sorry.
I think it is helium formation from hydrogen.
Hydrogen.
Yes.
In any star or other.
In all stars make helium out of hydrogen. They make it for most of their lives, for more than 90% of their lifetimes. The sun is making that all the time. And for 90% of their lifetime, stars only make helium out of hydrogen. Okay. So I don't know how that is related to the present talk, but that is the answer. All stars make helium out of hydrogen. Yes.
Yes, sir. So this is a question. Actually, I am not able to read. I'm going for that. I think it is how to measure size of exoplanet and what type of instrument used for it.
So I think this is what I already described in the talk, how to measure the size.
Yes.
So through the transit method, you can get the size of the planet. The instruments for the transit method are essentially ultra precise photometers, so which can measure light. So basically, you need extremely sensitive CCDs. And for the Wobble method, you need high resolution spectrographs. So you need things like, if you are familiar with these, like Febrile spectrographs or things like that, or grating spectrographs, diffraction gratings. Okay.
I think we are almost at the end of the talk.
Yeah.
Questions are over, I suppose, right?
Yeah. Last question.
Okay.
Is planet always stable or the change in time interval?
I don't know exactly what this means. By stability, if you are meaning stability of orbit, then on a short time scale, yes, planets are usually stable, but we do find evidences of planetary migration in different in distant stellar systems. So over time, planets can change their orbits, and they dynamically interact with each other, and it happens. It does not happen in our solar system much, but in other stellar systems, this has been seen.
Yeah, sir, the questions are in here. Thank you very much for the detailed information.
Yeah.
Okay, thank you.
Yeah. Thank you, Anwesh, actually very patiently answering these questions. Now I request our own Shekhar to present a vote of thanks. Shekhar, please.
Hello.
Yeah.
Thank you, Dr. Anwesh, for the wonderful lecture and accepting our invitation. Amish, you have taken very simple methods, and you almost given all the physical characteristics of exoplanets, how they can be detected. It was wonderful, and it is one step closer to
knowing whether there would be life someday on exoplanets. Thank you very much. And I would like to thank few more people here. I would like to thank the Jhunjhunwala College management for hosting this program. I would like to thank the principal, Dr. Himanshu Davda, and Director Usha Madam for their support and enthusiasm. I would like to thank the physics department of Jhunjhunwala College, HOD Rekha Madam, and Dr. Kiran, and everybody else in the physics department for their support. And I thank all the members of the Mumbai Sub RC. And at the end, I would like to thank you all the wonderful audience we had. Thank you very much.
Thank you, Shekhar, and thanks to all the audience. Thank you.
Thank you everyone. And just an announcement for the next lecture that is going to be on 2nd July by Dr. Sanjay Sani from National Center for Biological Sciences. He is going to talk about the mechanics of insects. It's going to be a very wonderful interdisciplinary talk. So I invite all the participants here to join this talk, the 7th of the series, which is conducted by Mumbai Sub RC, IAPT, and the RJ College Physics Department. So thank you one and all. Thank you, Anwesh, once again. Thanks.
Thank you.
Thank you.
Yeah.